Welcome to Lesson 7-4 in College Algebra. We are going to learn about inverse matrices and find another way to solve matrix equations. So in one of the previous lessons, we learned how to do the row reduced echelon form, and that is our REF on the calculator. That is one way to solve equations. And in this lesson, we will use another method using inverses. First of all, we need to learn what an inverse is, and we are going to use our calculators to help us out. Inverse matrices are useful in solving, and they're also kind of fun to do some decoding and encoding of messages. So I'll show you how that's done, and then I'll show you how to solve them. First of all, what is an inverse matrix? Think about inverses with basic numbers like you know. For example, like 3 plus -3 is 0, so it's the thing that undoes the other one to get us back to 0. With multiplication, it's what we would multiply by to get back to the identity, which is 1. We did identity matrix in the last lesson. So when you multiply 5 times 1/5, they kind of undo each other and bring you back to 1. And with matrices, remember that we have the identity matrix, which is 1, 0, 0, 1 if it's a 2 by 2. And so we basically want to find out what matrix would we multiply by to get us back to the identity. So it's undoing it. And you know, matrix multiplication is kind of complicated. So there's a formula for finding the inverse, but we're actually just going to use the calculator to help us out. There's also a method to do it. And the method is basically you take, we'll show you that in a little bit. I forgot. First, we're going to actually see if these are inverses. So in order to undo them, obviously some of the numbers are going to have to be positive and negative because we're going to add up to 0. You're going to have some fractions if you've got some big numbers to cancel things out. But just by looking at these two things, I cannot tell if these are inverses. So what we have to do is we have to check. We're going to do A times B and see if that equals the identity matrix. And we also have to check it the other way, because in order for them to be inverses of each other, they do have to be commutative. So if two matrices multiply in both directions and give you I, then they are inverses. So we can check that with doing simple multiplication. Not simple because it's matrices, but we're basically going to multiply our row by our column and add them up. Now I showed you in the last lesson how to do that on a calculator. So if you want to, you can put A and B in your calculator, or you can follow this multiplication to practice. And these are the steps that they got when they multiplied those out. This did come out to the identity. So now we need to check B times A. To check B times A, we're going to just go ahead and use the calculator. We could have done both that way to begin with. But when we check B times A, we also get the identity. So that means that matrix A and matrix B, these two matrices that we have here, are inverses. I can multiply them in any order and still come out with the identity matrix. To find the inverse of a square matrix, there's like a little formula you can do if it's a 2 by 2. If it's a 3 by 3, it gets a little more complicated. So there's one way that always works, and that's called to, it doesn't have a name, but where you basically augment your matrix with the identity, and then you solve it like with the row reduction method that we did by hand in previous lessons. So this is how you would set it up. You take your matrix A and you're going to augment it. So you're just going to draw that line down the middle with the identity. So here's matrix A and here's the identity. This is how you set up the problem. And then we're going to go through the steps, and I'm going to go pretty quick. So if I go too fast, remember you have a pause button, and that can be useful with online teaching. So we're going to go through, like, imagine that you just had this side and you're trying to solve it. Remember, the first step is that I want a 1 in this spot. So the first step I'm going to do is to swap these two rows and get my 1 in that first spot. The next step is I want to get these to be zeros. And to get them to be zeros, we're going to do that thing where we multiply a row by a number and add it to the other row. So that is shown here. And the steps are right here. We took 2 times. This is what we had on the previous page. 2 times the first row plus the second row, that gives me 0. So now I have my 1, 0, 0. The next step is to get a 1 here, which I already have. So I'm happy with that. Now I want to get a 0 here. And so the step to do that is multiply this by 2 and add it to that row, the entire row all the way across, and you're going all the way across into this other side. And what's happening as I turn this left-hand side into the identity, then this side becomes the inverse of my original matrix A. So this is the inverse of A, which I would call A inverse with the little -1 notation. So that's one way you can do it by hand. Now we do have calculators, and calculators make things easy. You can put matrix A in your calculator, and then on your working screen, you can just do A inverse. You do not want to do to the -1. That is not the right button. This button right here is the second, not second, it's below math. It is the button that says X -1, and it's the button above it is the one that says math if you have a TI. Okay, so you push that button. You cannot do to the -1 power. That's not going to work. Anyway, if you do that on your calculator, it will come out. So this is the inverse of A, which we could also call B, but because it's specific, you can do that. So let's just do this one on the calculator. Put this matrix in matrix A, and then type A inverse. And let's see what happens. You could also do it this other way if you want to practice the row reduction method. But I believe I've got, oh yeah. Okay, so when you do this, by the way, press that. Hopefully you get an error because we're on a new little section here that asks if the inverse even exists. Remember, not all matrices have inverses. So maybe you don't already know that, but not all matrices have inverses. So what you'll get is error, and if you have a TI, it will say singular matrix. Singular matrix means it does not have an inverse. So these are so complicated that there's not always an undo. An inverse. What you do get if you do it out the long way is you get to a point where you can't get a 1 here. It's just not possible because it disappeared. And once we have 0, we can't add things. That's not one of the rules. We have to multiply. And if we did add, we would get them here. So, so if you end up with error, you have singular matrix. That does not mean you still have to do this step because it just means there is no inverse. So because the bottom row has all zeros and we cannot get the identity matrix, then matrix A does not have an inverse. All right, so how can we use these to code and decode messages? So to try this out, we're going to take the statement, meet me for lunch. And the first thing you have to do is turn that into numbers. So A is 1, B is 2, C is 3, and so forth. And that's already been done for us. So meet me for lunch is these numbers down here. And 27 is a space. So it's MEET space, ME space for lunch. And that's what this says if we were to convert those using a very simple A is 1 code. Now, if we want to encode that message, we'll just need to multiply our matrix times these numbers. Now they're in sets of 3, and this is a 3 by 3. So we have to have them in sets of 3. That's why they're like this. We can do 13, 5, 5, and we can do one matrix at a time, which is what this next slide is going to show you. You can also pile them all up like this and just keep going on across. I need to erase that or I'm going to run out of room. Don't know why it's not erasing, but my eraser got small. Okay, so let's keep going. The next set is 15, 18, 27, 12, 21, 14, and 3, 8, 27. Okay, so you could do it all at once like this because you're going to take row times column, add them up. Row times column, add them up. And it would all work out the same as doing them individually. So I could just do 3 numbers at a time, or letters, whatever you want to call them, and multiply that by my matrix, and this would be my resulting encoded matrix or encoded numbers. So if I was sending this secret code to someone, I would send the message 8, 26, 39, and then we go over here, -35, 12, 46, 16, and you could send all that. if you do the multiplication, if you're doing this in your calculator, it's easier just to do it all at once. And this is a 3 by 6. So your answer is going to be a 3 by 6 message that you send with all these numbers in it. And then they would have to have our matrix to undo it. So this is putting it back together, and you can tell like MEET space, ME space, FOR space, like even the spaces aren't the same numbers because it's all tangled up in that matrix multiplication. So it's really hard to decode these without knowing what was used to encode them. So this makes them a lot more secure than other types of codes. So in order to decode this system, you have to know how to undo it. So basically, we took matrix A times my coded, or times my message, I guess, message, right? And I got my encoded message. And in order to decode that message, I would need to undo that. And we're going to kind of learn that in a little bit. But I need to undo that multiplication that I just did. So we're going to multiply it by its inverse. Whatever you do with matrices, you have to do in the same order. So since I multiplied this on the left, I would have to multiply this on the left. Basically, if you wanted to decode that message, you would do A inverse times your coded, no, that was encoded. I'm confusing it now, sorry. Encoded message, and you would get the decoded one. We're trying to decode it. If that didn't make sense, I'm going to explain it now with X's and Y's and numbers. So here we have X's and Y's and numbers, and we're trying to solve this system of equations, which if you remember back in 7.1 and 7.2, we were solving equations. In lesson 1 with elimination, and in lesson 2 with row reduction with matrices. So I can turn these into a matrix. The first thing I would do is take the left-hand side. They have to be in order, and pull out those coefficients, and that's going to be my matrix A. Pull out the letters, and that's going to be X, Y, Z. Now, the reason I can pull them out is because of multiplication. If I multiply this by this and tip it over, I get negative 2x plus 1y plus 2z, which is what that says. And the C, this will be my equals matrix. Everything over here on the right-hand side, that's going to be matrix C. So what I have right here, it is A times X equals C. Right? So if I multiply these together, I would get C. Now, if I want to solve that, we need to undo that. So this is where the decoding comes in. If I multiplied it by X and I want to solve for X, I want to get X all by itself, then I need to undo it by multiplying by A inverse. Because I'm doing it on the left-hand side, because there's already something on the right-hand side, I need to do it on the left. I need to do this on the left. So that's kind of one of the important things about this. Now we know that when we multiply a matrix by its inverse, we're just going to get the identity. And when we do the identity times anything, we get the anything. So this is going to cancel out, and we're going to get X equals. And we have to do the math to do the inverse of A times C. So using your calculator, you can just type in basically exactly this in your calculator. If you put this matrix in matrix A and this matrix in matrix C, you can type A inverse times C, and you will get the answer. Now I'm going to show you what they showed here, which is the same thing. They have A, which they didn't write out, times the XYZ matrix equals, and then we multiplied both sides by the inverse, and this is what you're doing, is the inverse of A, which we found earlier, times C. When you do that in your calculator, you're just going to get this simple 3x1 matrix, which is 16, 9, 14. And what we have left on the left side is our X matrix, which is XYZ. So very simply, X is 16, Y is 9, and Z is 14. So this is actually my favorite way to solve systems of equations with a matrix calculator. I don't usually use RREF. You can, but you don't have to. I just put all these numbers in matrix A, all these in, I usually use B, but you can use C, and then type A inverse C, and that concludes solving it. So that's all there is left to do. So to finish this lesson, we've just got an example. I'm going to go through it fairly quickly, but just to make sure you can set it up. So we have these 3 different type of calculators, and the production requirements of how much time and circuits and cases you need in order to make one of these. So we can turn this into an equation, and all this stuff is in the writing. We have this many circuit, this many hours, and this many cases. So we have these limitations that we want to use up all our stuff we can, but not go over. So let's solve this equation. What I would do in my calculator is in matrix A, I would put 5, 7, 12, 2, 3, 5, 1, 1, 1. That is matrix A. I'm not going to put this in my calculator, but matrix X is X, Y, Z. And I'm going to use matrix B this time because it's the next one down in my calculator. 134,000, 56,000, and 14,000. And then all I have to type on the home screen, go second quit, get back out there, do matrix A, names, with the little inverse button, and then I do like to hit times on this because I just like to see it there, matrix B, and press enter, and that is all you have to do to solve it. Let's go here, and there's my answer. This should be what your calculator spits out. That is your X, your Y, and your Z, so you can see exactly how many of each calculator you would want to produce to use all of your components. And that's it for lesson 7-4.